Calculus Curve Sketching Part 4, a selection of exam questions. Once again, I suggest that you pause and try the question yourself. It's not much good just watching somebody else do the question, so try the question yourself, knowing that you are going to be able to get the solution. And you can check as you go along. Let's look at this first question now. F of x is given as a function which already has its numerator and denominator factorized. No stationary points and a point of inflection at x approximately equal to 0,8. Question 1. Calculate the approximate value, y value of the point of inflection. So we're going to take that x value 0,8 and substitute it into the function. Negative 1,44. Question 2. Write down all intercepts for the axes. Well, that's x is 0 to find the y-intercept and y is 0 to find the x-intercept. And equations of the horizontal and vertical asymptotes. Vertical asymptotes is when the denominator of the fraction tends to 0, causing the function to tend to infinity. So the values of x that cause that. Horizontal asymptotes are the values of the limit as x tends to infinity. So the values of the function as x tends to infinity. Right, let's have a look. There's the y-intercept. Substitute x equals 0. You get y equals to negative 9. X-intercept, y equals 0. Factorize. We only have the top line. Notice x minus 6, x minus 1. That's all we need. We need a 0 at the top in order to have a 0 overall. X is equal to 1 or 6. Asymptotes. Vertical. We need either that or that to be 0 to make the denominator 0, to tend to 0 so that the function tends to infinity. Horizontal asymptote, there we are, we have the limit of the function as x tends to infinity. Now we need to divide through by the highest power of x amongst those terms there, which is x squared. We've ended up with 4 terms being fractions with x in the denominator, and as x tends to infinity, those are all going to tend to 0. So we have a horizontal asymptote of y equals 3. Graph of f cuts the horizontal asymptote at a point. Calculate the x value of this point. There's the horizontal asymptote. There's the equation of the function. There's the function's definition. If we equate the two, so that must equal 3 in order for that graph of f to cut the horizontal asymptote. So I equate the function to 3. Solve. Multiply up, divide by 3. Simplify and solve for x. 4 over 3. Hence draw the graph, a sketch graph of f, showing all intercepts, asymptotes, and the inflection point, as well as the point calculated in 3. There's our graph. Have a look at it, compare it to the working, make sure you understand it. Note I have not labeled all the points on the graph. All I do is label the strategic points. The vertical asymptote, the horizontal asymptote, the x-intercept there, the point of inflection, the point which we had to find in 3, and if there's no space, then we label with an arrow. Next question. The sketch shows the graph of the equation f of x equals 3x minus 9 over x squared minus x minus 2. A is the relative turning point of the curve. Another way of saying local stationary point, local minimum or local maximum. A is a local minimum. Give the equations of all the vertical and horizontal asymptotes of the graph of f. Well, once again, vertical, we want the function to tend to infinity, we want the denominator of the function to tend to 0, and it's the x values accordingly. Factorize, and we can then see the values of x. If x tends to negative 1 or 2, then the function will tend to infinity. So they're your asymptotes. Horizontal, we're going to find the limit as x tends to infinity. The highest power of x amongst those 5 terms is x squared. I must divide everything by x squared. And note that both terms in the numerator have an x in its denominator, which means that the numerator is going to tend to 0, which means the whole fraction tends to 0. Horizontal asymptote, y equals 0. Calculate the x-coordinate of A, which is the local minimum. Well, there we need to equate the derivative to 0 as a start to find the x value. Differentiation by quotient rule equals 0. Solve. Now that's just the numerator. Multiply out, simplify, factorize, and there are the x values. Notice that we have taken out the 5. The reason comes up in question 3, which says, explain why there is only one valid answer for question 2. Well, question 2 asks for the x-coordinate of A, and A has a particular position between the two vertical asymptotes, between negative 1 and 2, so therefore 5 is excluded. Next question. Given f of x equals 2x squared minus 7x plus 4 over x minus 3. Determine the equation of each asymptote of the function of f. Vertical asymptote, tend to 0. Horizontal asymptote, limit as x tends to infinity. And then have a look, x squared x, the degree of numerator is 1 higher than the degree of the denominator, which means that we have a linear oblique asymptote, which we can determine by doing a division. Probably better to do the division. There's also the formulae you can use, but the formulae aren't usually included on formula pages. So if you forget it and you don't know any other way, you've had it in an exam. As long as you remember how to do your long division, then you're fine. Asymptotes. X equals 3, tending to 0. None. If you divide by the highest power of x squared, of x being x squared, you're going to end up with 1 over x minus 3 over x squared here, and that will give you 0 in the denominator. So there's no limit exists. So there are no horizontal asymptotes. Now we do a long division. We divide x minus 3 into that numerator, and we end up with 2x minus 1 with a remainder of 1, which is still to be divided, so we'll leave it for somebody else to do. Now, as x tends to infinity, 1 over x minus 3 is going to tend to 0, which means overall f of x is going to tend towards 2x minus 1 plus 0, which means y equals 2x minus 1 is your oblique asymptote. Calculate the coordinates of any turning points of the function, correct to 2 decimal places, and by means of calculation, whether they're local maxima or minima. To calculate the x value of the turning point, we need to equate the derivative to 0. So let's differentiate that by quotient rule, put it equal to 0, and solve for x. Notice we need only thereafter equate the numerator to 0 simplifying, we end up having to use quadratic formula, which gives us an answer in surd form, but we have been told to give the answer correct to 2 decimal places, so we're going to go one further step and calculate it to 2 decimal places. Now that we have that, we now have to find whether they are local maxima or minima. So I now go to the second derivative. In order to make it easier for the second derivative, we know that that numerator simplified to that. So therefore we can see the derivative as that. That is a bit easier to differentiate now, once again using quotient rule. There it is. We don't need to simplify that. We're going to test 3,71 into there, and we're going to test 2,29 into there. The telling fact being whether it's positive, each gives you a positive or a negative. In fact, it's positive at x equals 3,71, which means it's a local minimum. Positive second derivative, concave up, means local minimum. At 3,71, take 3,71, substitute into the original, and it gives us 7,83, the y value. It comes out as less than 0, 2,29, so local maximum 2,29. Once again, substitute into the original to get 2,17, the y value, and there are our 2 turning points. Determine the x and y intercepts of the function f. Once again, x equals 0, y equals 0. There we are. Y-intercept, negative 4/3. X-intercept, when we equate this to 0, we can only worry about the numerator then. Well, that needs quadratic formula as well. So there's to 2 decimal places by quadratic formula. Sketch the graph of f. So there's everything summarized in order to give a bit of space for the graph. If you need to look, you could rewind back to the other working if you want to. And there is the graph. Notice every point labeled. There's quite a bit of space problem there, so I simply put the value further away and then just indicate with an arrow. Makes life much easier that way. And neater. Next question. Alongside is the graph of the function f of x equals 2x cubed plus 6x squared minus 25x minus 39 over x squared plus 6x plus 5. Dreadful looking graph. Determine the equations of the vertical asymptotes. Well, we're going to factorize the denominator, and we're going to find values of x for which that denominator tends to 0, making the function tend to infinity. So it's x equals negative 1, x equals negative 5, and there are the vertical asymptotes. Determine the equation of the oblique asymptote. Well, we're going to have to do this division again. Divide that third degree expression by the second degree expression. Notice there's only 1 degree difference, therefore once again it's a linear oblique asymptote, and we end up with that expression there. The answer was 2x minus 6, remainder x minus 9, which is still to be divided, so we'll leave it like that for somebody else to do. Now as x tends to infinity, being x squared below and only x above, this whole fraction is going to tend to 0. So overall, as x tends to infinity, f of x is going to tend to 2x minus 6 plus 0, which is 2x minus 6. Consider the domain x less than 0. Use the graph to determine the intervals where the second derivative is greater than 0. Well, what does second derivative greater than 0 mean on the graph? Concave up. Have a look at this curve. Concave up, cave facing up. Concave down, cave facing down, concave down. This one is only concave up between the vertical asymptotes, between those two numbers, negative 1 and 5. So that's your answer. That is the value. Concave up follows at negative 5 less than x less than negative 1. Next question. It is given that f of x equals 2x squared plus x minus 1 over x squared plus px plus 4. For what values of p will the graph of f have one x-intercept? Now if you look at this, that is a quadratic in the denominator, and there's a quadratic in the numerator. Now, it's only the numerator that counts if we're equating this to 0, because we need a 0 in the numerator to get 0. So that's the one there that actually determines your x-intercepts. Now the problem is this: we're going to factorize that into two brackets, giving us two x-intercepts. So how can we ever only have one? Well, the answer is simply this. There it is factorized, that in fact it's either got to have this bottom line, the denominator must end up with a 2x minus 1 as well to cancel the 2x minus 1 above, or an x plus 1 to cancel the x plus 1 above, thus giving us only the other bracket for one x-intercept. Now if we have 2x minus 1 here multiplying something, it must give us x squared plus px plus 4. Well, there's a 2x. What must x be here to give you x squared? Must surely be half x. There's a minus 1, and that's a 4. What must the constant be here in order to give us a plus 4 when multiplied by minus 1? It must be minus 4. So therefore we'll have half x minus 4. If we then multiply those out, 2x minus 1 times half x minus 4, we'll get the middle term, which will be the p-value. The coefficient of the middle term will be the p-value. And once again here, if I want to get the x plus 1 below, so it cancels the x plus 1 there, giving me only one x-intercept, to get x squared, there's an x, this will have to be an x. We need a 4 on the end. There's a 1, so this must be plus 4, so this must be x plus 4. So we multiply out x plus 4, and it'll give us the coefficient of the middle term, p. Here we go. Half x minus 4. If we multiply it out, the middle term is minus 8, 5x. So p is minus 8, 5. Or, if we go the other way, the second fraction, we'll end up with x plus 4, x plus 1 below, so that x plus 1 can cancel with the upper x plus 1. Multiplying that out, it'll give us a middle term of 5x, meaning p is equal to 5. One vertical asymptote. Next question. We need one vertical asymptote. Well, this is a quadratic. We don't know the value of p, but if it's going to give vertical asymptotes, it must either factorize or be solvable by a quadratic formula. We need that to tend to 0. But that'll give us two values, not one, a single vertical asymptote. So what is the only way that a quadratic, if equated to 0, can give you one answer? It's if the roots are equal, if it has equal zeros. In other words, it's got to end up being x plus 2 all squared. Got to have an x to get x squared. Got to have a plus 2 to give you the squared there. Right? Can be a minus 2 as well there, give you a squared there. So therefore, p is equal to 4. And p can also be equal to negative 4. So it's actually plus or minus 4. Given that p equals negative 5, solve for x if f of x is greater than or equal to 0. Or quite simply here, we've been given a rational inequality. There we are. We have 2x squared plus x minus 1 over x squared minus 5x plus 4, and they're factorized there. Now, do not multiply through. I'm reminding you, you should have done this before. Do not multiply through an inequality by a variable, because you do not know whether that variable is positive or negative, and whether it's going to change the greater than or less than sign around. So the only way is to find where it changes over from positive to negative, because at the moment it's a question of greater than 0, which means it needs to be positive. So we're going to look at the 4 critical values which make this fraction change sign, about which this fraction changes sign. And each critical value comes from where a bracket is 0. So half, -1, 4, 1. We're not saying make them 0. It's just about that where there's going to be a sign change. And we're going to put them on a number line in the correct order. So -1 the lowest, then half, then 1, then 4. Notice I'm allowing for the fact that x minus 1 and x minus 4 are on the denominator, which means the actual values themselves are excluded by having those hollow circles. I've included the minus 1 and the half, those are solid circles, because we have an or equal to. So they can be equal to, it can be equal to 0. It means that x can be equal to half, can be equal to minus 1. If there's just a greater than, then these would also be hollow circles. Now I'm going to test different areas. I'm going to test an x value in this area, such as -2, to see whether I get a positive or negative. From -1 to the half, I'm going to do the same. Half to 1, I'm going to do the same. 1 to 4, and above 4. That's what we get out of it. Now, I'm going to teach you to cheat here a little bit. You don't need to substitute in every region. Just be careful if you have a bracket squared. If a bracket is squared, it won't affect the sign. So if it's squared, then this rule works in a different way. But do you notice that these alternate? Positive, negative, positive, negative, positive, always. So what I'm going to do is I'm going to say, where can I find the most convenient number to substitute that's going to be easiest to substitute along here? And obviously the easiest number to substitute here is always going to be 0, between -1 and a half. So I substitute 0 into this fraction. And I end up getting a negative. So therefore between -1 and a half, I know it's got to be negative. And all I do is say, well, -1 means plus there, it means plus there, which means alternates back to a negative, then to a positive. That's the cheating method. Sketch the graph. All right, so there we are. Notice how we do that. So it's greater than or equal to 0. So I'm now going to look at it. I'm going to say, well, where is it positive? There. Which means from there to the left, so x is less than or equal to -1. It's positive there, which means from half to 1, including the half, excluding the 1. Well, there we are, half less than or equal to x, including the half, less than 1, excluding the 1. Or this region here, x is greater than 4. Sketch the graph of f, including intercepts with the axes and asymptotes. Stationary points not required, thank heavens. Now note this goes still with the p equal to -5. It's part of that question. Well, we're going to calculate the y-intercept, -1/4, by substituting 0. X-intercepts, we can equate the numerator to 0, factorize. There it is there anyway. Vertical asymptotes, well, if we have that as 5, there we are, 4 or 1, x equals 4 or x equals 1, there the vertical asymptote there. We're going to end up with a horizontal asymptote because we're going to have 2x squared, x squared. Now if we divide top and bottom by x squared, being the highest power of x, these two terms, those two terms will tend to 0 because they'll both end up being over either x or x squared. And we'll have 2 over 1, so therefore horizontal asymptote y equals 2. And there is the graph. Now you didn't have to find the stationary points, but you can ascertain and glean about what they'd have to be. This one you could have drawn right up to there, and that's fine. You don't know the stationary point, but you know that there's no x-intercept between 1 and 4. So that can't be the case. The other factor is here. This has helped you here too, you see. That's the whole idea. Less than or equal to negative 1. So it's positive, it's above the y-axis, above the x-axis, less than negative 1. It's above the x-axis from half to 1, half to 1, so it's above the x-axis, and it's above the x-axis above 4, which implies immediately, well, they are below the x-axis between negative 1 and a half, so therefore negative 1 to a half, there it is below, and between 1 and 4, there it is below there. Next question, match the following rational functions to the appropriate graphs A to F. So there's 6 graphs, of which 4 of them belong to those 4. Let's look at the first one. Now, you don't have to look at all the aspects of graph. Often there's something that can give you a bit of a hint as to which it can be. Now, when you see x squared minus 4, surely you think of something straight away from your grade 9 days. That's a difference of squares. It actually factorizes, and the x plus 2's will cancel, which means we'll only end up with x minus 2. So strictly speaking, this is f of x equals x minus 2. But hang on, remember, x can't be equal to 2. So have a look here. There we are. There's your linear function, your straight line graph. X can't be 2. Well, have a look. This one has the excluded 2. So that's your one for that question. Next one. Now, this question is very sneaky because you'll notice that all the vertical asymptotes are either negative 2 or 3. Negative 2s or 3s. So it's just done that to mix you up, you see. So here you could say, oh, well, x minus 3x plus 2, so therefore negative 2 or 3 are the asymptotes. That's fine, but have a look. Which one you're going to choose? There are 1, 2, 3 with negative 2 and 3 as vertical asymptotes. You could say x minus 2, well, that is the x-intercept is 2, so which of them has an x-intercept of 2? B does. Looks like C does as well, but it's touching there, which means if it's touching, you'd have to have an x minus 2 squared. But there's a 2 as well, so that 2 is not going to help us. So I'm afraid we're going to have to calculate a few more values. So there we are. Y-intercept 1/3. X-intercept 2, asymptotes there. Those all point to the graph just below. Have a look, they all match. Therefore, that's our graph. Next one. It's going to have a horizontal asymptote. X squared minus 6x plus 9. That's x minus 3 all squared. So it'll only have one vertical asymptote. So straight away it's a vertical asymptote of just 3. So it limits it down, but we have 2 with a vertical asymptote of just 3. Anyway, let's look at the other factors. There we are, have a look. I factorize it. We have the y-intercept, x-intercepts minus 3 and 2, asymptotes 1 and 3. Often it's better just to calculate everything and then just look and say which has all those functions. But remember, in an exam paper, these aren't worth a lot of marks, so just don't spend ages on them. That one has its matches there. There we are. So that's the answer to that one, E. Final one. Now I noticed something straight away here which is quite useful. That is x minus 2 all squared. So the x-intercepts are 2 and 2. I put that 2 grayed out because we don't need it there, but it's just interesting to know there are 2 x-intercepts which are equal, which means in effect that equal roots means the graph touches the x-axis at 2. And this is the only graph touching the x-axis. Oh no, that one's also touching the x-axis at 2, so we'll have to be careful of that. But if we look at the other facts, they all point to that one there. So there's our answer to that one. Last question. Function given as f of x equals x plus 4 into x plus 1 all to the negative 2. So it's given in a slightly different form. Determine the coordinates of the stationary point and prove that this is a local maximum. Right, so this is a case of differentiation and then second derivative. Very nice of them to give us in the form which makes it easier to differentiate. So there we are. There's the first derivative equal to 0. Invert the x plus 1 to the negative 3. And we solve and we end up with x equal to 1. Substituting back we get y equal to 2. So now we know that the stationary point is 1, 2. Now we have to prove that it's a local minimum. So we have to go to the second derivative. So we differentiate the derivative. There we are. And we're going to substitute the x value of 1 in. And when we do that, we get 3 over 2. Not that we have to show that. Mind you, we do, because it says prove that it's a local minimum. So we do. And it's greater than 0, which means it is a local minimum at 1, 2. Write down the equation of the oblique asymptote. Right, so we're going to have to get it. We already have it in that form. Have a look here. X plus 4 over x plus 1 all squared. You see, it's already in the form you need to see the oblique asymptote. 4 over x plus 1 all squared will tend to infinity. It will tend to 0 as x tends to infinity. Therefore, the whole function f of x will tend to x plus 0 as x tends to infinity. That was very easy. That must be worth only a couple of marks in the exam.